First of all, hello, everyone. My name is Eric Kirsten. I'm a senior advisor to CodeSmith. I've been a part of CodeSmith for about 8 years, and I have the pleasure of emceeing this tonight, which we're all very, very excited about. First off, I want to thank everybody at CodeSmith, Agnes, Laura, everybody on the team who's just absolutely amazing and has put together just an incredible speaker series at CodeSmith's DSML program. And it's just the quality of the speakers, like the one we have tonight, which I'm really excited to introduce, has just been a lot of fun to learn from and to experience these talks. So Grant Ingersoll is just a different level person. He's been a fractional CTO several times over in his career. He's serving as a fractional CTO right now. And if you don't know what that is, it's someone who basically comes in and is kind of takes over the CTO role and kind of handles it and then hands it off to another CTO. It's a very, very, correct me if I'm wrong, Grant, but the people I know who've done this have described it as a pretty intense experience, and you have to be a pretty high functioning person to be able to handle that. And he's done it repeatedly in his career, which is just mind-blowing. He also served as the CTO of Wikimedia, which is just massive, by the way. And he was the founder of the Mahout machine learning project for the Apache software. I actually wrote it down because I wanted to make sure I said it right. Which, for those of you who don't know, is the largest open source foundation in the world. And that's just awesome. So that entrepreneurial spirit is alive and well. His expertise on everything he's going to be talking about tonight, as far as search, AI, natural language processing, etc., is just runs very, very deep. So because of that, he's been a public speaker on this topic. He's an instructor on this. He has written so many articles in all of these areas. And then something very, very true to all of our hearts, obviously at CodeSmith, he has his own podcast and website, Develomentor, combining developer and mentor, I assume, develomentor.com. Please check it out. And the podcasts are just awesome, where he just focuses on tech careers, and kind of helping people along their pathway. And I think, someone at his level doing that is just absolutely awesome. So anyway, we're extremely lucky to have him. And so I'll hand it over to Grant and let him take it from here. And there's time for questions at the end, if that's cool with everybody. If you don't mind holding your questions that come up in your head, we'll have some time for that at the end. So everyone, please meet Grant Ingersoll.
Awesome. Thank you, Eric. And really appreciate the warm welcome and the support in inviting me here tonight. And I'm excited to be here. I've gotten to know CodeSmith a little bit over the past year, and really excited about what you all are doing. I'm a big believer in what education and learning, especially for later in the career, or folks who perhaps went to college and did one thing and then decided they want to join in on the tech side of the house. I'm a big believer in the opportunities that folks have to do that, and CodeSmith, I think, does a wonderful job of bringing that forward. So today we're going to talk about using machine learning and natural language processing to create modern search and discovery experiences. So what that means for me is I come primarily from a search background. I've done a lot of things by hand, if you will, through rules and all of that. And these days, of course, the question comes forward is, how do we use all these advances in machine learning and natural language processing? Since you're in the data science and machine learning cohort here at CodeSmith, or at least I'm assuming many of you are, you're no doubt aware that there has been nothing short of revolution in this space in the past, so let's call it 5 to 10 years. I think I gave my first talk on deep learning back in 2013. And of course, the techniques go way back before that, but thanks in many ways to the big data movement, as well as to the access that we all now have to cheap computation and GPUs and all of this data, we're in many ways able to tackle problems that for a long time, or at least in the scope of most of my career in this space, have felt pretty unsolvable, or at least required a whole lot of human intervention. And I lost my focus, so there we go. You could even argue, I think, with the advent of sites like Hugging Face, where basically the world shares natural language processing models and other models. And then, of course, the thing that's taken the world by storm in the past, I don't know, what do you call it, 6 weeks or 3 months, ChatGPT, as well as a number of other frameworks that make it way easier to process text. We are in many ways in a golden age of natural language processing and text processing. I often think like many programmers who are starting today are essentially AI natives when it comes to developers. Whereas folks like me, you know, it wasn't just there at our beck and call whenever you wanted it. And to put that in context, I don't say this lightly, because I've been through AI winter. I got my first job in NLP in 1999, and I have written more regular expressions to process text than I even care to remember. And moreover, in no small part, thanks to all of this data, I think we are also witnessing a pretty significant shift in the search and discovery space, away from classical methods of retrieval to newer methods that better support the output of all of these new machine learning techniques. If you think about it, ChatGPT caused one of the world's largest companies, not just search companies, but largest tech companies, to completely react unlike anything that company has ever reacted to in the past, right? And of course, along the way with all of these new techniques, there's been a lot of new software, new engines that have come along, places, things like Pinecone, Quadrant, Weaviate, Gina, Vespa, name a few, are all starting to take center stage in this market of how do we make this data searchable and findable for our users, all while also helping, or at least claiming to help us as users get to the true meaning of what we care about. And of course, in hopes of not being left behind, perhaps some of you are familiar with, quote unquote, the old guard of search engines, things like Elasticsearch, many of you are probably familiar with, things like Solr, Lucene, or OpenSearch. These are all essentially derivatives of this Java search library that I started my career on called Lucene. They have all also added support for this new type of data, this dense vector data, which if you've done any machine learning work or done deep learning or neural network work, you are familiar with as the common output of all of these new approaches to machine learning. So you might even be wondering, as you think through like perhaps what you have at work or what you are studying in at Codesmith, or just coming across as you travel the internet, what should you be thinking about getting that, you know, what should you be doing next to improve your search? Or what should you be learning about? Should you go to your company and say, hey, I think we need to throw out this Elastic thing and bring in Weaviate or Vespa or one of these other things? Perhaps if you dug a little deeper on this, you might say, hey, maybe I can blend these together. Maybe I should use the plugins from OpenSearch or Solr or whatever. And at the end of the day, you're kind of asking this classic engineering question of what works, or what usually happens, what doesn't work. I want to pause there, though, and take a little bit of a step back, perhaps pump the brakes, as they say. I'm going to try to answer, at least the best I can, some of those questions, and perhaps at the end have some room for some of the others that you might have. I'll give you some recommendations, but I want to take a little bit of a step back and talk a little bit about what I consider to be some first principles in search, especially for this audience. I don't know how many of you have worked on search or worked on search-like problems before. And so I want to, you know, set the stage, if you will. And I want to start by asking, first and foremost, what problem are we trying to solve with search. If you go into the academic side of the house on this kind of stuff, those people who study search, they would say that we are trying to solve a user's need for information, presumably so that you or me or someone else can take some sort of action. But as the text here says, it may not always be clear to the user or to us as engineers or product managers or whomever is involved in this, exactly what that user is after. And I want you to think about that for a moment. Think about, I don't know, the last 10 searches you conducted on Google or DuckDuckGo or ChatGPT or whatever. Are you actually able to articulate what you want? Or even better, can you articulate why you think you need that bit of information you are seeking? And then when you actually get the results, how do you really know that that thing that you think is the answer is actually the answer, or even a part of the answer? Let's then think a little bit about how we go about trying to solve that problem, because it's a really hard problem. I've spent my entire career on it. It's endlessly fascinating, and there are so many different avenues you can go down and specialize on in this field. So let's talk about, at least in my mind, what I see as the three primary areas that are really at our disposal as application builders or product managers when it comes to satisfying this quest that we are all after around information needs. The first thing we can start to think about is, are there smarter ways that we can process our content? In other words, can we give the machine a deeper understanding of that content? So this is commonly, as you can see, referred to as content understanding. We've got all of this text coming in, these images, these tables, these charts, these Excel files, these PowerPoints. Let me enrich that data as it's being brought into my engine so that I can make better sense of it. And of course, at the end of the day, a search engine's job is to rank things. It's to say, hey, CodeSmith user or CodeSmith learner, when you put in this Google for JavaScript or Kubernetes or whatever it is, tell me the things that I really need to know. What are the most important things? Or at least you hope it's telling you the most important things. These days, if you're a little bit cynical about some of the major search providers, you might just say, oh, well, they're just trying to show me ads. But at the end of the day, like, if they're not at least attempting to tell you this is the thing that matters about this search, then they're really fundamentally failing at it. And I want to highlight that specifically because unlike in the database world where you're traditionally saying, give me all things in this set that match the set criteria and then sort them, ranking is a little bit of a different problem. Or you might think of it, if you come from SQL land, as you're saying something like select star from table, where sort by importance. Whereas in a database, you might just say sort by price. We can do that in a search engine too, but really what we want to say is sort by this ranking factor that often includes lots of different attributes, things like how many keywords match, or how close our text embeddings are to the query, or how popular a particular document is on a social network, right? So this idea of asking the engine to say, give me the top 10 or the top 20 is a really important part of the search engine. Finally, when it comes to thinking about and improving a search engine, you can ask the question, can we improve our understanding of what a user is asking? We call this, as you might guess, query understanding. And you also might guess by the size of these images that I'm a pretty big believer, thanks in no small part to my work with Daniel Tunkenlang, on query understanding. But we really can't skip over these other things like ranking and content understanding in the context of using machine learning and NLP for solving these problems. And the reason I say it that way is because these days, even with all of the advances, it's not as simple just to say, hey, I'm going to throw all of my content into a transformer-based deep learning engine like a Weaviate or whatever, and just have it do its magical thing. And all of a sudden, all of the problems around solving search are solved. So let's dive in, because there are actually ways that you can apply across all of these different pieces in order to make for a much better solution for your users. So let's get started by looking at what is probably the most obvious choice for applying at least the natural language processing piece of that. And I'm primarily in this case talking about text-based or human written content, right? You know, all of the web pages, the documents, the PowerPoints, the Word, etc., that we've all written. Pretty logical place to start with natural language processing because it contains a whole lot of text. So to put it simply, content understanding is this process of representing each piece of content in the index so that to make it findable. In other words, we're going to try and slice and dice up this text into a way that our search engine can then be better queried. You can do things like indexing text documents by their words or tokens. You can, indexing text documents by their words or tokens in an inverted index is perhaps this most naive form of content understanding. And if you're not familiar with what an inverted index is, it's essentially the thing that gets in the back of, the old school physical books where you could go and say, this word appears on this page. Of course, a search engine has a lot more fancy ways of doing that, but that's essentially what an inverted index is. And as you may have seen, if you've used things like Lucene or Solr or Elasticsearch, these things all have pretty sophisticated text analyzers that can tokenize, they can stem, they can deal with different languages, all of that kind of stuff. But they're pretty simple string processing steps that really are only the beginning of content understanding. And when you think about what makes for a robust content understanding, it really uses a combination of both holistic and reductionist techniques to categorize content and recognize entities in order to transform this raw content into something that is more useful in terms of representing it in the index. Because at the end of the day, most of these engines look at individual tokens and want to be able to treat them as units that are then findable. There really are two main approaches to content understanding these days with NLP. Content classification really is about applying labels to say that, hey, there's this thing like, if we read a document, we might say this document's about technology, it's about machine learning, it's about sports, it's about economics. And so we assign these labels to it, and then we can index those labels, but we can also do things like mark up or annotate individual parts of the text such that we can then identify things like named entities in them. And then you might be able to say, find me all documents that reference Google, right? So this is the idea that you're using the engine for content annotation. So these are two common tried and true techniques to apply to them, to apply to your text as it's coming in. And of course, we've long been using rules, machine learning and NLP to do all of these things. But of course, these days, we're often using word embeddings. If you're not familiar with this, although it sounds like you've had a little bit of an overview of this in the past, and presumably if you're in the data science track here, you're doing some deeper work on this. But effectively, word embeddings are mapping tokens or spans of tokens or even entire documents into a vector space, which is, just a fancy way of us being able to calculate a mathematical distance between these documents. such that we're trying to make that distance correspond to some semantic meaning or semantic difference in meaning. And word embeddings really just emerged out of the linguistics field on all of this stuff. And the basic intuition behind them, if you want to simplify it or share it with your boss or put it in layperson's term, is it's really just about, this old saying of a word is characterized by the company it keeps. The really cool thing in this space is these word embedding techniques have advanced at a pretty fast pace in the last few years. There's things like Glove, Fast Text, BERT, Elmo. If you go on Hugging Face, it seems like there's a new one of these almost every day. And the cool thing is you can build on top of the work that other people have done in the space. And of course, these embeddings can be super useful for both supervised and unsupervised ML. So typical supervised applications, if you're not familiar with this, you need some notion of labeled data, you need some notion of ground truth. And then you can do things like content classification and annotation on them. But it turns out, at least especially in the search space, you can also use these embeddings for unsupervised applications, things like generating synonyms or even measuring how similar documents or queries are. And the nice thing is you can kind of bootstrap these without labeled data and then pretty effectively build search off of that. And again, we're not even talking about using this in say a dense vector engine. We're just purely talking about, I already have an engine in place. One of the things I want to do is enrich my content. So I'm going to run it through some of these machine learning techniques. But of course, you can also just directly search off of these things. And that's really where all of these new search engines we talked about earlier come in. So effectively, you're taking your model or you're using a pre-trained one, or you're fine-tuning a pre-trained one, and you're just going to process all of your documents through, and then you're going to shove them into this dense vector engine like a pinecone. And away you go, and then you can start to just query it, and effectively, just like in classical search, you're doing a distance calculation in a vector space in order to then retrieve back these top results. It is worth noting here that pretty much all of the old engines have added support for dense retrieval. So Elastic, Solr, OpenSearch, Vespa, all have support for both of these models. And it's also curious to note, just in case you're wondering whether all of the old approaches are being thrown out by these new engines, most of the new engines like Weaviate, et cetera, Pinecone, are all adding classical search capabilities to them as well. But that's enough on content understanding. You could do a whole PhD on content understanding and still not cover all of the things. I just hope to give you a little bit of a taste there. But let's move on and talk about ranking. And it's really worth noting here first that ranking does not equal relevance. So if you've ever dealt with search, you probably have heard the term relevance, and maybe you haven't so much thought about it as ranking. We tend to, as users, think about, is this thing relevant to me? And if you read academic papers on it, it talks about relevance, so on, so forth. But just to dissect this a little bit, ranking is what the engine does. So the engine is going to take in your query and it's going to spit back the top 10 results. It is a list of elements. It's a ranking on that. Relevance is you. What do you, the user, care about? It's you deciding that the third element is the most relevant thing to you, or the fifth, or all 10 of them, whatever it is. Engines are ultimately trying to provide that ranked list of results that are relevant, but of course, they aren't always successful. These days, most major search engines, the way they approach these problems is by using what's called a multi-phase ranking strategy. And they apply specifically this thing called learning to rank. So in other words, they're going to use machine learning to try to figure out what that ranking list should be. And the reason why it's multi-phase is because you can actually stack these things. You might have a really fast baseline ranker that gets you, say, 1,000 results. Then you might have a simple machine learning model that re-ranks the top 100 of those. And then you might even have a more sophisticated model that maybe just re-ranks the top 10. Or a rumor even has it that some of the really big providers in this space doing online search at internet scale have models specifically for 1 versus 2, right? And so that's why this is called multi-phase, or sometimes it's called cascading ranking. When it comes to this idea of learning to rank, there are really 3 main ways to do this. You can do point-wise, which is basically a prediction question for your ML model. What should the score or the rank of this document be for this query? You can do what's called pairwise, which is basically, if you think about, if I have 10 results, I can just say, compare 1 to 2, 2 to 3, 3 to 4, 4 to 5, on down the chain as deep as you want to go. And you're kind of always asking which one of these should be ahead of the other one. And then last but not least, you can try to predict the whole list. Say, hey, I'm going to try to rank this whole list, and I'm going to put it all in context of each other. And of course, you can dig in on all of these at a much deeper level by going and reading the literature and trying out some of the learning to rank modules that come with these search engines. In order for you to do learning to rank, you really need a handful of things. First and foremost, you need judgments. This is a supervised task. And by judgments here, they can either be implicit, like what did a user click on when they did a search? What did they hover on? Where did their eyesight go? What did they buy? What did they put in their cart? Whatever you have where you implicitly try to understand, hey, because this user clicked on this and they spent a lot of time on that page, probably relevant to them. Or you can have explicit judgments, namely you can crowdsource this and say, hey, for this query and this document, was this relevant to you? And so you can then gather all of that feedback and you can plug it into your learning to rank system. In order to do the implicit, you will, throughout all of this, need query logs. And those query logs need to not only have the positive examples, but you also need to have negative examples. And you need to know where in the list they occurred, as well as any other metadata you have. So in other words, not only do you need to know, hey, a user clicked on something, but you need to know they clicked on the 5th thing. And by definition, if they clicked on the 5th thing that as their first thing they clicked on, that means they skipped 1 through 4. So that likely means that 1 through 4 weren't as good. And then you need some metrics. If you're not familiar, you can go look up around things like precision recall. MRR here stands for mean reciprocal rank, essentially 1 over the position they clicked on. And then there's a much deeper metric here called normalized discounted cumulative gain. It's a bit of a mouthful, but it essentially bakes in a discount based off of how far down somebody had to go to click. So effectively, it's rewarding higher up in the result list. And then, of course, as with all machine learning systems, it's really nice to have an A/B testing framework so you could try out one model versus another model and see which ranking approach performs better. When it comes to all of this, of course, state of the art these days are deep learning approaches, but I will make the case here that you can actually do still really well using older techniques, things like XGBoost or even logistic or linear regression. And I'm a big believer that you should always start with those as a baseline and then prove why you need to go above that in terms of time and effort and money and scale and all of those kinds of things. The important thing to note with LTR, because it is a re-ranking technique, In other words, I first have to go get a set of candidates that I can then rank. Your baseline here matters, right? Like in order for a result to be re-ranked, that means it first has to be ranked. The cool thing is out of the box in most of these engines, there's a pretty tried and true approach to that baseline ranking called BM25. And you'll often even find in the academic work here that it's a real challenge to beat that, even by state-of-the-art systems without a whole lot of work. So this BM25 thing is probably a, I don't know, 50 or 60-year-old approach at this point. It was created in the early 70s or mid 70s, and basically looks at things like the term frequency and then how often words occur in the overall set of documents. And so that core scoring algorithm can be pretty hard to beat, especially if you have somebody who's good at tuning that thing. And then I would encourage you, if you want to dig deeper on ranking and things like learning to rank, there's a nice white paper called Click Models for Web Search. And this really is about how do you leverage your query logs to better investigate and understand and better leverage what your users are telling you. And so there's a lot of different ways you can deploy those click models into your learning to rank system. Let's continue on though, because I want to talk a little bit about query understanding as well, and then we'll get to these recommendations. But query understanding, as I talked about earlier, is really this process of transforming a search query. If you think about it, often just one or two words, maybe it's a whole sentence or a question, to better represent the user's true intent, if you actually could know it. And it's interesting because it's a bit different from everything else we've looked at so far, this idea of content understanding where you have long form text or ranking. Whether we've looked at this at indexing, retrieval, or ranking, we've pretty much been focusing most of our time on what the engine is going to return back out. Whereas query understanding really focuses on the beginning of the process, the query. It's about what happens before the search engine retrieves and ranks results, namely the searcher's process of expressing that intent, and then the search engine's process of taking that intent and translating into something that is machine usable. It's really focusing on that communication challenge. And this is one of the things that's always fascinated me with search, because I think I am not going out on a limb here to say that search is the only interface where your users get to, in their own words, tell you what they want. If you think about most other parts of the application, a user is clicking, but in order to click on a link, etc., like the application designer has to lead with, here's the link I'm going to put on the page. Whereas with the search box, it's just an empty box. And then it's up to the engine to figure out and interpret that. So to put it another way, this job of query understanding is figure out what they want, regardless of what the best result may be, or even whether there is any results or there are good results in the index. And indeed, sometimes it's a great way for an application to communicate that it knows what you care about, but that they don't actually have it. So in this example, B&H Photo, the user typed in iPhones, and B&H just simply says, hey, we know you're looking for an iPhone, but we don't have it. Netflix does this as well. You know, you go and put in that mainstream popular movie that's not on Netflix. They say, hey, sorry, we don't have that movie, but here's some movies that are like that. Right, that's query understanding in a nutshell. And at the end of the day, you're still satisfying that user, at least by the sense of saying, hey, I don't know what I don't know. And that can go a long way. So let's look at some of the techniques for query understanding. And some of the most popular and practical techniques fall into this kind of broad class of strategies that we would call query rewriting. Query rewriting automatically transforms the user's queries into a better representation of that intent, as well as doing things like fixing spelling and all of these other things that kind of are like essentially normalizing or canonicalizing the user's query into something that is going to be more useful. So for instance, if my user query on the left is all things upon news, I gave this talk first at a conference called All Things Open, hence the example. I might automatically correct that spelling error, but I also might do all kinds of other things to that query by understanding what that query is about. So this on the right is effectively a way of rewriting. The piece down here of boosting by recency is actually picking up on the fact that the user is looking for news. In other words, they just don't want general information about this conference. They want the latest information on it. So perhaps I should boost or sort by recency when it comes to this content. Digging in a little bit deeper, query expansion is primarily one of the techniques, which is really about how do I broaden this query by adding additional tokens or phrases or other things. And these additional tokens may be related to the original query term as synonyms or abbreviations, acronyms, etc. Or if the original query is an and of tokens, in other words, the users have put together a bunch of things and said, I want all of these things to come together. Query expansion might also add in some other approaches to that, like combining those synonyms with or clauses. So for instance, if somebody's looking up for a blow up jacuzzi, you might expand the blow up to be blow up or inflatable, and then and it with jacuzzi or hot tub, because those are synonyms. Another good example of this type of thing is Apple doesn't call their laptops, they call them portables. So if you put in MacBook Pro laptop, it probably would expand that out to also include the word portable, so on. And so these are all techniques that are geared around bringing back more likely relevant results. In other words, we're trying to increase recall. And there's a lot of different ways you can do this. You can create dictionaries, you can obtain a thesaurus, you can use your prior queries, you can use embeddings. All of these things can be leveraged in order to expand a query and essentially increase the chances that you're going to find good results for the user. We can also do something that kind of feels like the opposite of query expansion. We can relax our query. So instead of adding tokens, we're going to remove them. And specifically, query relaxation increases recall here by making optional or removing tokens that may not be necessary to ensure relevance. So for example, a search for cute fluffy kittens might return results that only match fluffy kittens or cute kittens. And query relaxation also allows us allows retrieval to ignore query tokens that really are optional. So for example, the query Microsoft Windows laptop, that really in many ways conveys the same meaning as Windows laptop, but it is likely to exclude results that don't include the redundant word Microsoft. So query relaxation can also help when there are no results or few results that completely match the user's information needs. So for example, if somebody says king size sheet set with cats and dogs, in many cases, returning results that are at least partially matching that user's need, i.e. king size sheets, will be better than not returning anything at all. In many cases, you might also want to increase precision in your results. In other words, making sure in, say, your top 10, you have highly relevant results. And so sometimes we need to have an understanding of that multiple tokens from the user actually represent a single semantic unit. For example, dress shirt, in the query white dress shirt, right? treating this segment as a phrase, i.e. rewriting the query so that dress shirt has to match tokens in that order. They can't just be near each other or, within or in reverse order. That can really help improve precision, and it can avoid matches for white shirt dresses, for instance. Or it can ensure that searches for things like hot dogs don't return overheated dogs. And query segmentation is related, when you think about it, to tokenization as well. We can think of these segments in many ways as larger tokens. But we generally think of tokenization as something that the analyzer handles at the character level for both queries and documents, while query segmentation is query specific and does take place at the token level. Continuing on, just like in content classification, query classification is doing much the same thing. We're taking a query and we're trying to map it to one or more categories from a predefined set of labels, such as, for instance, product types. Implementing query classification really does, though, require addressing a pretty key challenge. Queries tend to be short, i.e. just maybe 1 or 2 tokens. And so how do we classify queries when we have so little input to work with? So let's think a little bit about some of these usages, and I'll come back and answer some on that question in a moment. But given these classifications of queries, we can then use our labels. So we just took OtterBox Pixel 6, and we now know that it's a cell phone accessory. We can take those labels and we can do 2 things with them in the actual search. We can, as you see on the left here, filter out search results and say, hey, no, I don't want any of those. I don't want any results that aren't accessories. Or maybe a little less draconian on that, we could just boost up results that do have category matches. But just in case we didn't get the classification wrong, we're not going to completely remove all of these things. And of course, you could also even just restrict down your search and say, I'm only going to search within a particular area or a particular subset of categories. Excuse me. So when it comes to this notion of query classification, there really are 3 main approaches we can do here. Yes, you can do manual labeling, i.e. you have users or engineers or people on your team go through and say, this query is this category. We can use heuristics, things like regular expressions or rules that say, hey, anytime you see the word OtterBox, because we happen to know they only sell accessories, if that's actually true. If the word OtterBox is in the query, we're gonna apply this label of accessories to it. And as you all are probably here for, and in the classes here for at Codesmith, we can use machine learning. And all of these approaches quickly grow in both complexity, but also in scalability. And so kind of how can you start to think about these things, or how do you bootstrap? Assuming you have query logs, they often look like or have a distribution like what you see on the screen here. Namely, they are a power law. This intuitively makes sense. Most users come in and ask the same, like on Google, will ask the same queries over and over again about whatever the trending event is, whether it's balloons over the US, or it's some celebrity or who did something stupid. Like, that's often going to be repeatedly asked over and over again by your users. And so these are called head queries. And one of the easiest things you can do is classify them by hand. It's a great way of bootstrapping your entire system. And it has this huge benefit that those queries probably make up somewhere between 50 and 80% of all your queries. And so with, I don't know, a handful of hours of work, maybe a couple of days, and then deploying some keyword matching string processing techniques, all of a sudden you've improved your most popular queries, which, oh, by the way, probably also correlate with where you make most of your revenue. Gee, boss, look how smart I am. We're now classifying our head queries and giving way better results. And it really doesn't take that much effort, right? To recognize, for instance, that something like a Sony digital camera should be mapped into something like the digital cameras category. As we go down to the right on this graph, you start to get into the torso queries, right? These are still popular, but not quite as popular. And depending on the site and what you do, they might be somewhere in the range of, let's call it, I don't know, 15 to 50% of your queries, maybe less, maybe more. And one of the cool things you can do here is actually use some rules if you want. You can use heuristics. In fact, we can often churn the short length of our queries to our advantage, because here string matching and regular expression approaches are unlikely to stumble, right? They're going to pretty much get it right on these short queries. And so you can do even better if you have this historical searcher behavior that you can mine, like using the dominant category associated with a query's clicked result, right? So you get all these query logs in, you take for any given query, the most popular item or the items that are clicked on for that query, and then you transfer that click onto the category of that document. And then you add up how many of those are, and now you know what is the most dominant category. And then you just, start using that category probably as a boosting factor. And then it gets interesting and also gets hard, right? Like typically you're not going to get into what's called tail optimization or looking at the tail until you've successfully gone through and handled your head queries and your torso queries more effectively. But there's actually a number of things you can do here. And it really becomes a question of how much you're going to invest in this area, depending on how important search is in your application. If you're a large consumer e-commerce site or a website, you're probably spending a fair amount of time on the tail, because the tail is probably still lots and lots of queries. And just even moving a little bit of the tail, you could probably see some pretty interesting results. And I'll leave you with one last thought on the tail, because two last thoughts. The tail, all of this stuff, you can start to use the head and the torso to then train machine learning models that ideally can then generalize to the tail. And one last thing I want to leave you with on this idea around thinking about tail queries is they are often very highly correlated with head queries, believe it or not. So even though they're less frequent because they have unique terms in them, when you look at the subset of terms within them, they often have head queries in them. So for instance, one data set I studied from a large e-commerce retailer, upwards of 50% of the tail, we're talking millions of queries, upwards of 50% of the tail queries actually had correlations to the head or torso. And what that meant was we could actually use that to the advantage. What's an example of this? If a head query is iPhone, a tail query might be torso as well, but tail query might be silver, 64 gigabyte, Apple iPhone 14 with 3 cameras and something else, and a case. Like that might be a tail query. And as you probably just parsed in your own head, well, yeah, there's iPhone in there, there's case, there's all these other kinds of things, right? And so when it comes to query understanding and machine learning, there's some really awesome capabilities out here with machine learning that are really fast and effective. Like I said, that pivoting of query through the document to the category and learning a classifier off of that requires almost zero training, zero bootstrapping of training data. So what you want to do is make sure you have good query logs. And then I would say start with this category classification of queries associated with click documents, and then go and train a machine learning classifier on top of that. And here again, you don't have to start with the expensive techniques. You can start pretty lightweight and you will probably see success. No, just keeping an eye on time. I know we started a little bit late, so I still will have some time for questions, but I want to finish up with a few recommendations. I like to frame these things in the place of now, next, and later. What should I do right now? What should be not too far off? And then, hey, maybe when it's, becomes more important or we get through all these other things, we'll do later. On the now front, first and foremost, if you don't have your logs, your metrics, and your testing house in order, don't bother. And that's probably true of all machine learning systems. In fact, I was just talking to a client of mine today where they couldn't reliably tell what model was in production. They did not have good version control over their models. They did not have a good way of measuring baselines, and yet they were still deploying models. They just didn't have any accountability around it. The second bullet point I cannot emphasize enough. I learned this a hard way as a startup founder, especially as a back-end engineer who was so focused on all the plumbing that I lost sight of the fact that a good UI or user experience can go a long, long way. I love to tell the story of a large US retailer that added over $100 million in revenue in one quarter just by adding type-ahead autocomplete. Type-ahead autocomplete in search land is pretty much an engineering task. It doesn't require a whole lot of fancy PhDs or natural language processing or anything. It just requires a bit more hardware and some smarts around how you process those queries. Next thing I would do is query understanding, like I just said with that classification. And then I would probably dig into LTR. And then from there, you can kind of cascade down. What is probably state of the art these days is actually a hybrid model. There are places where dense vector search just simply doesn't work that well, or perhaps put in a better framing where the classical approaches work much more effectively and much more cheaply. And then you can use things like embeddings for the annotation and classification. And then maybe at some point, go and switch your engines or at least start using these plugins. But you can even apply a lot of these, like I said, these neural techniques on upstream aspects of the search problem before you actually deploy a quote unquote semantic search engine, which of course leads a little bit into the pros and cons of some of these engines. And of course, maybe in a year, this slide will be completely outdated, or maybe it already is on some of these bullet points. I don't keep track of every last feature that these vendors are providing. The pros on these neural things, is it's pretty much where the money is all flowing these days. These engines are really good at doing things like word sense disambiguation and synonyms. Like that's all kind of given to you as part of the way these embedding models and transformer models are built. They tend to do better at longer queries and in question answering systems. So like the ChatGPT or others where maybe you're matching against FAQs. And of course, they often can handle multimodal content. Namely, you could put in a text query and get back images because there's this notion of image understanding that's happening as well, or vice versa. You can query by an image and then retrieve back text documents. Some of the cons, there are challenges with explainability. There's also challenges with how these engines do ranking and how do you figure out where to cut off the results, where do they not become relevant. There, of course, is a lot of compute costs, although, because the money is flowing into this space, those costs are coming down. There is some domain portability, perhaps issues, but again, people are working to solve this. Namely, can I take a model that's trained on this particular type of data and deploy it on a different type of data? What kind of work do I have to do to make that domain portable? At the end of the day, I think we live in a hybrid world. And so a really, kind of simple architecture for all of this stuff. User query comes in. We do some form of normalization of that query, some pre-processing to essentially, correct for spelling errors and bad punctuation or things like that. We then feed it into one or more classifiers. You can kind of think about these classifiers as doing both making strategic classifications, i.e. what type of approach should I take in order to do search? And then they might also do tactical things like the query segmentation or the query rewriting, some of those pieces. And of course, you can have multiple models. You can, these things are typically very fast and, run in the order of a few milliseconds, especially because they're on very short data. And then you're going to feed that through rules engines. All of these engines still have a notion of rules. Sometimes you just need the hammer that says, if a user does this thing, we don't trust the rankers, we don't trust the query classifiers, we just want this result to come back because one of our clients is paying us $1 million to make sure their result is on the top. And then we can actually fan this out across all of these different approaches. You can send it to good old-fashioned Elasticsearch and its classical approach. You could feed it into the neural engine and get back answers there. You might send it off to a question answering system, or perhaps you'll use something like a Wikidata or a DBpedia, some type of Sparkle interface or knowledge graph type interface, and you might do inferencing on those kinds of things. And then you feed that back up into the aggregator, you apply machine learning again to join them, and then you spit them back out to your users. So with that, I'll leave you with where you can get a hold of me. So
thank you so much, Grant. That was a really great presentation. I learned a lot during it. I love to ask this question to people. Well, the question I normally ask is, if you had advice for your old self, right? The Grant that's first getting into NLP, what advice would you give?
Oh,
and then I have a follow-up question, because I know that might not be super applicable since everything has changed.
First, wow, way back. I mean, so I started on, this will date myself, but I think my first NLP job was in 1999 doing cross-language search. So we took in English queries and searched like Japanese documents and French documents. And, I mean, there's kind of a meta level answer to that, which is like, I thought I was underqualified. I had huge imposter syndrome on it. I did not think I would even get the job. So there's that part of it. So part of me would probably just say, hey, go for it. You can do this. But at the time I wasn't sure. I think one of the things that's guided my career and I've seen go wrong for a lot of people in technology is they stop learning. And I know that sounds cheesy, especially when it's kind of bread and butter and apple pie, motherhood and apple pie for a place like Codesmith. But like there have been so many iterations, especially in this field, where, for instance, venture capital stopped funding it, where people said, oh, search is a solved problem, or NLP, oh, nobody does that anymore because it's all rules based and we can't figure out how to make these engines better at it. And so people went away from it. And then it took, kind of some of the diehards, for lack of a better word, or the people who still believed, who were willing to question those things. And so they had this learning mindset around it. And so they went and dug in on new approaches and new techniques, or they took old approaches and applied them in new ways. So I think, that notion is, I think I would just tell myself to double down on that. Right. And it took me a while in my career to realize like those are the things I actually cared and valued about in a job and in the people I work with. Because early on, you're often so busy paying the bills and all of that kind of stuff. These days, I mean, so my son's a computer science major, and I think, I think a lot about like this AI native developer, AI native product manager, or whatever the role is, and how like, so then the question becomes is what can we unlock for these next level of features and capabilities and applications, and what can you build given something like a NLP model on Hugging Face is just a given, and it does a pretty darn good job at it, right? And so that excitement, is just carry that through in your career as well. I don't know if that's what you were looking for, but hopefully that's helpful.
Honestly, I couldn't have asked for a better answer. Yeah, thank you very much.
The other thing I would say is I do always find there is value in understanding the I don't know if plumbing is the right word, but like the base classes of these systems. So even though like these statistical methods, maybe they implicitly understand things like parts of speech and punctuation and all of these kinds of things by the way they calculate their stats. Like I think you as an engineer and or builder of these systems, having an understanding of the constituent parts at the human level, if you will, is and will always be useful because it allows you to reason about why and how these systems work or don't work.
Wonderful.
Amazing.
Thank you.
Yeah, thank you for that, Grant. Kaju, do you mind kicking off for yourself? That's great.
Yeah, thanks, Eric. Hey, Grant, thank you. So I was wondering, way back in the beginning, you were saying that some of these search providers, they're adding back in classical patterns of searching, and I'm just wondering why that is the case. I mean, you might have covered this. Might have not understood fully well, but thank you.
Yeah, no, that's a great question. So I made the comment, kind of the semi tongue-in-cheek start or opening to this was like, hey, there's all this money going into the Weaviates and the pine cones, and then the old guard, if you will. It sounds weird to call like Elasticsearch old guard, given it, really came into its own 6 years ago, but they're all adding these newer techniques as well, right? And so it comes down to this kind of notion of use a screwdriver to screw in a screw and use a hammer to hammer a nail, right? It turns out like when you look at things like query logs and the types of ways of retrieving information for a user, we'll go back to a little bit of this diagram here. So for instance, if a user on an e-commerce site types in an integer, literally the only thing in the query box is a bunch of numbers. The statistical models really don't know what to make of that unless you have to do a fair amount of work to do that. Whereas a classical approach, you would almost immediately recognize that that's probably a SKU or a product ID, and then you would just search the field and you would have an exact match on that actual thing. And there's no such thing as synonyms for SKUs. There might be related product SKUs, that kind of stuff. And so there can still be some ambiguity there. The other thing, like these engines often struggle with post results filtering. They often struggle with things like faceting or aggregations or post result processing. They often also struggle with pre-result filtering or kind of narrowing down the space based off of things you might already know about the search. And of course, like I take that with a grain of salt because this is changing very rapidly. But like at the end of the day, like the engines like Lucene they almost get a bad rap by just being called a search engine. Because if you look underneath the hood, they actually have some really advanced data structures and algorithms that are highly optimized around retrieval of data and then processing of that data. So for instance, one of the things that brought Elastic to fame was really, this Kibana and the dashboarding and all of the roll-ups and calculations that it does in order to build these dashboards on top of, say, for instance, your logs. Well, it turns out like all of those techniques are pretty common, like low-level database techniques that these engines like a Solr and Elastic, OpenSearch, Lucene provide. And it turns out that there's a lot of problems you can solve with those types of techniques. They're also really good at compression. They're really good at counting things that are defined by that ranking problem. And so like these engines are realizing in order to solve the full suite of search problems, things like type ahead, spelling correction, the faceting, the aggregations, the paging, the re-rank, all of those kinds of things, you need a host of different techniques built on top of that. And so I think that's what's driving a lot of that is like, how do we build a complete application on this engine, not just how do we do semantic search on this engine? And that's why I even go back to this idea that UI and UX goes a long way. If you start with design, human-centered design, like what do my customers want? Instead of you then being the engineer that's like, hey, this is the thing that I use to solve every problem. Instead, you put on your hat that says, I'm here to solve these problems. What is the best tool to go do that? And I think that then leads into an evergreen career where you're always able to work on interesting things as opposed to just working on the one thing that you happen to learn at any particular point in time. Does that answer your question?
Yeah, exactly. Like I put in tracking numbers in Google all the time and it does the job. And I mean, this would be just, with this semantic search.
And it's a great interview question. Like, there's often the question of what happens when you type in google.com, right, as a system design question. But I think, if you're in our land or my land here for this, what happens when somebody types in a tracking number into Google search? How does it even know it's a tracking number? Right? As opposed to maybe it's a credit card number. Like they look pretty similar. Obviously, Google isn't going to return credit card numbers for you, but you get what I'm saying. Other things, for instance, that a lot of these search engines have, I will put any of these engines when it comes to like geospatial search up against any GIS system, like Solr, Elastic, etc., have very capable like bounding polygon type capabilities, i.e. find all the things that fall into this spatial area. And it doesn't even have to just be like latitude, longitude. I'm talking n-dimensional spaces. Those kinds of things can solve some really interesting problems. And if you Google, for instance, you can solve like, how do I return results of restaurants that are open right now? Turns out it's actually a pretty hard problem, but search engines have actually built-in functionality that can do that kind of thing.
Gotcha. Thank you.
Grant, we can't thank you enough for joining us tonight. This was absolutely awesome. It's an honor to have you with us at Codesmith.
Thank you, Eric, and thanks to Codesmith, and best of luck to all of you. I hope some of you land in the search space.
Awesome. Thank you. Cheers.
Cheers.